All right, so welcome everyone to this seminar on geometry with symmetries. And today it's my great pleasure to welcome Luigi Vezzoni, very good friend and collaborator. And he'll be talking about Calabi-Yau problem in HKT geometry. So thank you, Luigi.
Okay, thank you for the introduction. Thank you for the invitation. I'm very happy to have the possibility to do this talk. And also I'm very happy to meet some friends, even if in a telematic way, but yeah, it's very nice. And I'm going to talk about something called HKT geometry, and the HKT geometry means HyperKahler with torsion. So there are these geometric structures are a generalization of the HyperKahler structure. And the results I'm going to describe, I obtained this result in collaboration with Giovanni Gentili, who is a PhD student in Torino, and some of them also with Lucio Bedulli. Okay. Okay, the idea here is starting from the very beginning is the definition of HyperKahler structure. So the definition is very natural. We consider a smooth real manifold having a real dimension for n. And by definition, an hypercompact structure is a tripole of compact structures, which here I denoted by ijk. And these three compact structures satisfy the quaternionic relation, which can be described in this way. So ij is minus ji, and the ij and the minus ji are the last compact structure k. So this is the definition of hypercompact structure, and by definition, a hypercompact manifold is a smooth manifold together a hypercompact structure. And on a hypercompact manifold, there is always a unique connection, which in this talk is denoted by nabla. And this connection was first described by Obata in 1955, and today is called the Obata Connection, and is an affine connection and is determined by these two relations. So the first one says that the connection preserves the hypercompact structure, and the second condition is that the connection is torsion-free. So the theorem is that there is only one connection which satisfies these two relations. And this connection is very good for having some geometric information about the geometry of the hypercompact manifold. And here there are two examples. For instance, the case where this connection is flat. So the case where the curvature tensor of this connection is vanishing corresponds to the case where the manifold is locally isomorphic to the standard model h to the n, and here h is the quaternionic vector space. And I mean, the manifold where the Obata connection satisfies this condition are usually called locally flat. I mean. And another interesting case is when the holonomous disconnection is contained in the Lie group of S, L, and H. And this condition implies that the canonical bundle of Mi, so of M and one of these three complex structures, is holomorphically trivial. In general, it's not true the converse here, but the converse is true in the HKT case, which I describe in the other slides. Okay, and after the definition of hypercompact structure, there is the natural definition of hyperHermitian metric. So I consider a hypercompact manifold, and I consider a Riemannian metric. And the Riemannian metric is called hyperHermitian if it's compatible with all these three complex structures. So it's compatible with I, J, and K. So it's Hermitian with respect to each one of these complex structures. And of course, it determines three fundamental forms, which here are denoted by omega I, omega J, and omega K. and all of them are real to form, and each one is of type 1,1 with respect to its complex structure. And I mean, it's possible to combine these forms in order to have a form which here is denoted by capital omega, which is of type 2,0 with respect to I. And the form capital omega is defined like in this way, like omega j plus I omega k. And this form capital omega satisfies two nice relations. So the first relation is this one. So if we apply j to capital omega, we obtain the omega bar. And this form is positive in this sense. So if we consider capital omega of z, j of z bar, we have something positive for every vector field of type 1,0 with respect to I, which is different from 0. What is good is that every form capital omega of type 2,0 with respect to I, which is co-real and positive, determines the metric G. And so we have a bijection between co-real and positive 2,0 form with hyperHermitian matrix. And this relation is analog to the one in Hermitian geometry, where there is the correspondence between Hermitian forms and Hermitian matrix. So the idea here is that we can forget the metric and work with the form capital omega. Okay, and now the next step consists in recalling the definition of the Bismuth connection. And the Bismuth connection is a special connection which is defined in general in Hermitian geometry. And what Bismuth proved is that if we have an Hermitian manifold, then there is always a unique connection, which is here is denoted by nabla I, which satisfies these two relations. So the connection preserves the Hermitian structure. And if we consider the torsion of the connection and we compose the torsion with the metric, we obtain a tree form. So this is the unique connection which satisfies these two relations. And this connection is, is a special connection in the sense of Gudoshan. So it belongs to a fine line of special Hermitian connections described by Gudoshan. Okay, and now I can give the definition of Hkt manifold, and the definition was introduced by Owen and Papadopoulos for physical reasons. But today, these manifolds are important also for geometric reasons. And a hyperHermitian manifold is called Hkt if the Bismuth connections determines by Gi, Gj, and Gk, so the three Bismuth connections are the same. Okay, this was the original definition given by Owen and Papadopoulos of Hkt manifold, and of course it's more general of the definition of HyperKahler manifold, where these three Bismuth connections are the Levi-Civita connection of the metric G. And yeah. And a little bit later, Grancher and Poon proved that the Hkt condition is equivalent to require that the form capital omega is D-closed, where D here is the D operator with respect to the complex structure I, so the first complex structure. And this is the definition of Hkt manifold, which is usually considered today. So when I refer to an Hkt manifold, I mean to an hyperHermitian manifold where the fundamental form capital omega is D-closed. Okay, there is, there is many analogies between HKT manifolds and Kahler manifolds, where the rule of the Kahler form is replaced by the form capital omega. For instance, Verbisky developed a Hodge theory on HKT manifolds in this way. So by starting with an hyperHermitian manifold, it's possible to consider this complex. So the forms are P0 forms with respect to I. And then we have two operators here of degree 1. So the first one is the D operator with respect to I. And the second the derivation is this one. So it's consistent in considering j to the -1 d bar j, where d bar is again induced by I. And this complex has some analogies with the Dolbeault complex in complex geometry. So for instance, these two conditions are satisfied. The square of these two operators are vanishing, and these two operators anti-commute. So it's possible to consider their cohomologies and study their cohomologies and deducing some invariants by considering these operators. Well, and as I said before, usually having in the hyperHermitian case that the holonomy of the Bismuth connection is contained is SL and H in the hyperHermitian case is not equivalent to have the canonical bundle holomorphical trivial, but this condition becomes, these two conditions become equivalent in the HKT case. Yeah, in 2004, Banos and Swan prove that in general for in the HKT case for the form capital omega, there is also a local pluripotential in this sense that the form capital omega can be always written as Ddg V for some, this locally, for some smooth function V on the manifold. So again, this is analog to what happened in the Kahler case, where the Kahler form is always locally, can be always written as dd bar V for some function V. Okay, and this suggests to consider the definition of a plurisubharmonic function in this context. So this function in this context are called quaternionic plurisubharmonic functions. And the function is quaternionic plurisubharmonic if omega plus ddj phi is positive in the sense I described before. And so we have, we have the space of quaternionic plurisubharmonic functions, and every quaternionic plurisubharmonic function determines a new form capital omega, and from here we have a new HKT structure on the manifold, which is still compatible with the starting hypercompact structure. Okay. And another analogy with the Kahler case is a theorem of Lejny, Gransharov, and Verbisky in 2017, when they consider an eight-dimensional HKT manifold, which is also SL2H. So SL2H means that the holonomy of the Obata connection is contained. They consider an hypercomplex manifold, which is also SL2H. SL2H means that the holonomy of the Obata connection is contained in SL2H. And they prove that this manifold is HKT if and only if the cohomology group of the sheaf of the holomorphic functions on the manifold is an even dimension. Sorry. Okay. Okay, examples of HKT manifolds. So the basic examples are given by HyperKahler manifolds, since every HyperKahler manifold is natural HKT. Every hypercomplex manifold is always locally HKT, so we don't have local obstructions to the existence of HKT structures on hypercomplex manifolds. And here is a class of examples, which is, I mean, a little bit involved, and essentially this construction is due by Joyce. And this construction consists by starting by a compact semisimple group G, having rank R, and then what is possible to prove that if we consider this group and we consider the direct product with a torus of the right dimension, then this product has always a left invariant HKT structure. So it has a left invariant hypercomplex structure, and it has a left invariant metric, which is HKT with respect to the hypercomplex structure IJK. And this construction can be generalized to homogeneous spaces, and this was done by Offerman and Papadopoulos a little bit later, the construction of Joyce. And another intrinsic class of manifolds admitting HKT structures are, I mean, nil manifolds, or more general quotient of Lie groups by compact lattices. And for instance, for nil manifolds, it has been proved that in some cases they have a left invariant HKT structures. And there are some, the first examples, I think, were given by Dotti and Fino, and then there are some characterizations by Barberi, Dotti, and Verbisky. And there are some more involved examples and difficult examples of HKT manifolds. For instance, some examples even simply connected was constructed by Swan by using a construction which is called a twist construction, which the starting point consists in considering a manifold with an action of a torus. Okay, and there are also examples of compact hypercomplex manifolds without HKT metrics. So there are no local obstructions, but in general there are some global obstructions. Okay, this slide is for introducing the Calabi-Yau problem in this context, and also for speaking a little about of special HKT metrics. And I say that an HKT metric is balanced HKT if the HKT metric is also balanced with respect to the first complex structure. And I recall that balance means that the fundamental form omega I is co-closed, instead than closed as in the Keller case. And Verbisky proved that the balance condition in HKT geometry can be characterized in terms of the form capital omega, and the metric G is balanced HKT if and only if the top power of omega is holomorphic form. So omega to the n is d bar closed. And this gives an obstruction, and this implies that every balanced Hkt manifold has the canonical bundle holomorphical trivial. So the question now is if every Hkt manifold with holomorphically trivial canonical bundle admits a balanced Hkt metric, at least in the compact case. And so far, all the known examples of compact Hkt manifolds with holomorphically trivial canonical bundle have a balanced Hkt metric. And so the natural conjecture introduced by Alesker and Verbisky is the following: that given an Hkt manifold having the canonical bundle holomorphically trivial has a balanced Hkt metric. So now in the next slide, I show that this conjecture can be considered as an analog of the Calabi conjecture in HKT geometry.
So Luigi, quick question. The canonical bundle has dimension 1.
Yes, complex dimension
It's
bundle.
it's a complex line bundle, right?
Yes, yes.
And what do you mean by holomorphically trivial? That there is a holomorphic section, or?
Yes, it has a nowhere vanishing holomorphic section.
Okay.
Okay.
And
It
is
is more,
related to the SLNH holonomy? Or?
yes, in the HKT case is equivalent.
Ah, it's the same. Okay.
Yeah,
Okay.
in the HKT case is the same. Yes, exactly. And the holomorphically trivial is more than trivial because maybe it has a nowhere vanishing section, but maybe this section is not holomorphic. Okay. Okay. So what is one of the possible strategy to prove the conjecture is introduce an analog of the Mohr-Ampère equation in this case. And so the approach is the following. So start with a compact Hkt manifold, which is also SLNH, which is equivalent to require that the canonical bundle is holomorphically trivial. Since the canonical bundle is holomorphically trivial, we have a holomorphic volume form with respect to I. And this holomorphic volume form here is denoted by theta. Okay, and then we consider this Calabi-Yau problem. So, omega is the starting Hkt form. So we consider omega plus ddj phi to the n. And we impose this is a times theta, where a is a positive constant. And the unknown is given by phi and a. So phi is a smooth function and a is a positive constant. And the condition on phi is that phi is also quaternionic plurisubharmonic. So omega plus ddj phi is positive. Okay, if we find function phi which satisfies this condition, we have that omega plus ddj phi is a new Hkt structure such that omega plus ddj phi to the n is holomorphic, since theta is holomorphic. But for the Verbisky theorem, this is equivalent to require that omega plus ddj phi is balanced. And so if we prove that this equation has always a solution phi, then we have a proof of the Alesker Verbisky conjecture. And so the new conjecture, which implies the previous one, is that in the compact case, for every theta, this equation can be always solved. And here the equation is rewritten in this way by replacing the rule of theta by e to the f omega n in order to have f as the atom instead than theta. Okay, so this equation here is called the quaternionic Moivre-Ampère equation. Okay, and the rest of this talk is to have some to describe some partial results in the direction of proving this conjecture. Do I have a question, Ramiro?
But what about the holomorphic condition in this rewriting of the conjecture?
Yeah, because theta is holomorphic. Theta is holomorphic.
Yes, but in the conjecture you don't see that, right?
I mean, you're right.
How you have to add that there is
this conjecture implies this, because if this is true for every function, then in particular it's true for the holomorphic volume form.
So it's more general.
It's more general. Okay. You're right.
Okay.
Yeah, but the idea is actually that I mean, this is true for every function. So in particular, this is more general and implies what we want. Okay, and the first observation is this equation is elliptic, because if we consider if we linearize the equation, we have that the linearization acts on phi in this way, as described in the last line, and this is an elliptic operator, which usually is denoted by the Laplacian, even if it is not the Laplacian, the Riemannian Laplacian. But yeah, I use this condition. This notation is standard in HKT geometry. Okay, here is a description of the local model. So what I mean, one of the main problem in studying this equation is its local formulation, because in general there are not the real quaternionic coordinates, and so it is not properly the determinant of a matrix or something like that. This is a little bit changes if we consider the standard model. By the standard model, I mean the ball in the H to the n. H is the quaternionic vector space, which can be identified with R to the for n with 3 standard complex structures. And in the standard model, I consider G the Euclidean metric. And here there are some, natural derivations, which are described by these relations. And here I, J, K, and the quaternion numbers. They are not the real derivations, but they have some analogies to the derivations. For instance, if we consider the bracket between the derivative with respect to Q alpha and the derivative with respect to Q bar beta, this is vanishing. And when we consider the previous problem in this particular setting, we have something which really recall the complex Moivre-Ampère equation. So we have the determinant of a matrix which equals to the datum. And here we have to consider determinant of a quaternionic matrix. This is something called the Moore determinant. And I mean, in this particular setting, the problem is understood by Alesker in 2003. Even if this is more analytic than geometric, because we are in an open set, while we would like to study the problem in a compact case. But in this standard model, we have a local formulation which is for many reasons similar to the complex case. Okay, here there are some partial results to the quaternionic Monge-Ampere equation and to the conjecture. So it's known that solutions to the quaternionic Monge-Ampere equation are unique. So everything here is in the compact case. I only consider the compact case. And yeah, the natural approach for proving the conjecture is try to imitate Yau's proof of the Calabi conjecture, and so to use the continuity method. And the hard part consists on having the a priori estimates. But something was obtained. For instance, the C0 a priori estimate was proved in several steps. A first proof was given by Alesker and Verbisky. A second proof in a more general setting was given by Alesker and Verbisky. And quite recently, Rocca gave a new proof in a very general case. So the C0 estimate, a priori estimate, is completely understood. What about the other estimates? They seems to be very difficult. Something is proved under some extra assumptions. And for instance, Alesker proved a very nice result when there are strong assumptions on the manifold. And the strong assumptions are the following: the manifold is supposed to be locally flat, which means that locally is isomorphic to the quaternionic vector space. In this way, it's possible to use some sort of quaternionic coordinates. And also here, what is needed is existence of a background hyperKahler metric, which is compatible with ij and k. And in this case, Alesker proved that the solutions to the quaternionic Monge-Ampere equation satisfy this bound. So the Laplacian has an upper bound. And I mean, what Alesker also proved is that in the locally flat case, if we have an upper bound of the Laplacian of the solution, we have also the CK bound of the solution for every K. So putting together these three results, we have this theorem of Alesker, which says that the quaternionic Monge-Ampere equation can be always solved in the locally flat case, admitting the existence of a background hyperKahler metric. And very recently, this result of Alesker was generalized by Dines Rocca in a very nice paper. And they generalized the theorem by removing the locally flat assumptions from the theorem of Alesker. So they proved that the quaternionic Monge-Ampere equation can be solved in a very compact compact Hkt manifold, having a background hyperKahler metric, which is compatible with the hypercomplex structure. Okay, now I can describe a little bit our work. So I consider this conjecture in some specific examples, and I started by considering the equation on 8-dimensional non-abelian nilpotent Lie groups carrying a left invariant HKT structure, and these Lie groups are classified, and they are only 3. And here there is a very rough descriptions. So they are, all of them are a direct product of an Heisenberg group by error. And Rn. And all these three examples are principal torus bundles, and more precisely our principal bundle, our principal T3 bundle over a T5. I mean, not the three groups, but the quotient of these three groups by a co-compact lattice. And so we have this nice bundle, bundle structure. And what is possible to do is study the equation when the datum f is invariant by, the datum f is invariant by the action of the fiber. In this way, the equation can be described as an equation on the base. So we have an analytic equation on the base, which is a 5-dimensional torus. And with Giovanni Gentili, we proved that under this assumption, the equation can be always solved. And this equation is, this case is far from the case, is far from the theorem of Alesker and the theorem of Soroka and Dineb, because these manifolds do not carry any hyperKahler metric. Okay, and here is the rough idea of the proof. So by considering the work of Alesker, what is enough is to prove an upper bound to the Laplacian of a solution. And the equation can be explicitly, the equation on the base can be explicitly described when all the assumptions are used and when the equation is simplified, what we get is this equation, which is displayed here on the base. So this is not a real Mogenthaler equation because it's not a determinant of an nation or something similar. But this equation has some nice relations. For instance, here we have two products and if we consider the sum of this part with this part, we have 2 plus the Laplacian, and this really helps for studying this equation. And then here there is some negative part, and here we have the derivative with respect to the last coordinate, and we have and the other coordinates here appear in each term, and here we have the square. And we obtained the estimates of the Laplacian by applying the maximal principle of this auxiliary function capital phi, which is given by the Laplacian of phi plus 2 times an exponential. So the exponential is e to the mi phi, and here there is a suitable choice of mu, which is a constant. This equation here is quite similar to an equation I got in the past by working with Yang Li and Fino and Simon Salomon for studying a completely different problem, but in a torus bundle, we got a similar equation. Very recently, Elia Fusi, who is another PhD student in Torino, proved that the solvability of a large class of elliptic equation on torus. And this class of elliptic equation is very nice because it includes this equation, also the other one I got in the past. So this case, this case is now, we completely understood this case when the datum is invariant by the fiber, and now what we are trying to do is to removing the symmetry on the data. By considering something which is not invariant by the action of the fiber, and this is more difficult to handle, but I think it's possible to say something in the future. Okay, and a very basic observation is that if we consider this equation and if we assume half is not depending on the last variable on the last variable x phi. What we get that we can use the ansatz that also phi does not depend on x phi, And in this way, this equation becomes extremely easy because all these terms cancel out, also this term, and so we get the standard Poisson equation. So if we see this manifold has a T4 bundle over T4, we have something which is extremely easy, which is the standard Poisson equation. And this was the initial observation for considering a much more, at least from the geometric viewpoint, involved situation by considering a compact Hkt manifold equipped with a foliation which is Hkt, in the sense that everything induces a nice structure on this foliation, and having the right rank, which in this case is for n minus 4. And what we prove that if we consider a basic function, then the equation becomes something, not the Poisson equation, but something which is similar to the Poisson equation, because we have the Laplacian of phi plus an extra part, which is quadratic, and the gradient of phi, and equal to the e to the f minus 1. And actually, this equation can be proved, can be solved by combining some classical results. But I mean, this approach can be considered interesting because it includes some interesting case, at least from the geometric point of view. For instance, SU3. SU3 can be included in this setup. And okay, now maybe I don't have time enough to describe SU3 in detail, because I want to tell a little bit about the dynamical approach. But SU3 can be fit in this description, and it has a natural left invariant Hkt structure, and it has also natural foliation, so we can apply the previous approach, and when you apply the previous approach, in this case we get this foliation, which is in the last line. So we have the Laplacian of phi minus the norm of the gradient to the square of the norm of the gradient equal to the datum. Well, so also in this case, the idea is considering this approach as an initial approach, and then in order to remove the symmetry from the initial datum, and understanding the general situation in these specific examples. Okay, another approach I introduced in order to study this problem, in order to study this equation, is the parabolic approach. Also, this approach is very natural, because what is possible to do for the classical Calabi-Yau problem, there is the proof of Yau, and then there is also the approach to the problem by using the Ricci flow, or the more specific, the parabolic Moivre equation. So here we studied the problem by introducing a geometric flow, and the geometric flow is the one which is described here. So starting by a compact Hkt manifold, and given the datum f, we consider this geometric flow, which is given by here, phi t means the derivative of phi with respect to t. And here there is this equation, which is analog to the parabolic complex Moivre equation in the complex case. So we call this equation the parabolic quaternionic Moivre equation. So, and the result I obtained with working with Lucio Bedulli and Giovanni Gentili is that in the same assumptions of Alesker, so when the manifold is locally flat, and there is also a background HyperKahler metric, then this flow has always a long time solution. And when this solution is normalized, then its normalization converges in C infinity topology, to a solution of the quaternionic Moivre equation. So this gives another proof of Alesker theorem, and maybe something which is a little more general, because it also gives a description of this flow in the Alesker case. So, and the strategy of the proof is, so this result is analog to analogous to other geometric flows in Hermitian geometry. And here there is a list. There is the classical result of Zhao about the interplay between the Ricci flow and the Calabi problem. There is a result of Gill about the parabolic Moivre equation, a result of Sun for more general flows, and a result of Feng To in a very general situation. And here there is the strategy of the proof. So the proof is more or less divided in 5 steps, and not in all the steps use the assumption, but we use all the assumptions only in a specific step. So the first step is having a C0 bound on the derivative of the time derivative of phi, and this is very, very easy. Can be directly deduced from the equation. And the second step is more or less an observation. When we have this C0 bound on phi t, we can deduce a uniform bound on the oscillation of phi. So the oscillation is the maximum on phi minus the minimum phi, and the oscillation, of course, is only along the spatial variable. So this is again a function on t. Okay, and here there's the first step, and this is the step where we use all the assumptions. So we use the existence of a background HyperKahler metric, and also the local flatness of the local flatness of the hypercomplex structure. And here is where we use in order to obtain a uniform upper bound of the Laplacian of phi. And here the Laplacian is computed with respect to the background HyperKahler metric. And after that, we can use a sort of general result of Junction 2, and well, we can deduce the CK. We can deduce the CK estimates of the function. So this step is the only one where you use all the assumptions. So these 4 steps together give the long time existence, and the last step is about the convergence of the normalization of the function. And here in order to do this, we introduced a sort of Mabuchi functional in HKT geometry in order to adapt a proof of Fong-Sturm for the parabolic Moivre equation in our case. And in the next slide, I give a short description on this step phi, because just to introduce this Mabuchi type functional in HKT geometry. So the idea is more or less the following. I assume to have a compact Hkt manifold, which is also SL and H, so such that the canonical bundle is holomorphically trivial. And so consider the form capital omega, consider omega to the n, and consider the d bar of omega to the n. And this this is can be written as theta bar wedge omega to the n for some form theta of type 1, 0 with respect to I. So the metric is balanced if and only if this form theta is vanishing. So it's very natural try to minimizing this theta by using a functional such that its critical points are the metric having this theta vanishing. And here we can use something which is called the Ddg Lemma. And by using this Ddg Lemma, it's possible to prove that the dj theta bar is ddjh for some function h, which is smooth. So this h is a sort of a potential which depends on the Hkt metric. And then we can consider the Hkt Mabuchi energy in this way. So, and well, and here we have this capital theta which we needed in order to integrate. So this is a complex volume form which is independent on phi. And this function is analog to the Mabuchi energy in the Hermitian case. And what is possible to prove is that its critical points are balanced Hkt metrics. So what we want to do is consider the gradient flow of this functional in order to detect the balanced Hkt metrics on the manifold. And it's not difficult to prove that its gradient flow is given by these parabolic equations. So the time derivative of omega t is equal to minus the derivative of j theta bar. So this is an analog of the this is an analog of the Calabi flow in the HKT geometry, where this theta bar replaces the rule of the d bar of the scalar curvature. And so this is an analog of the Calabi flow, and this is, I mean, we use this functional as last step in the previous proof, but now I think this functional can be used in order to say something more about the existence of balanced Hkt metrics on Hkt manifolds, but this is still in progress. Okay, and usually the Calabi flow and the Mabuchi energy are related to the Hermitian geometry of the space of plurisubarmonic functions in Hermitian manifolds, and here it's possible to do the same by considering quaternionic plurisubarmonic functions. So I starting with compact SLNH Hkt manifold, and by fixing theta a complex volume form as before, we can consider the Mabuchi energy adapted to our case. So given two functions to function in H, which means that they are quaternionic plurisubarmonic, we can consider is product given by in this way, as described here. So this is a Riemannian metric because of this product depends on phi, which is a quaternionic plurisubarmonic function. And so this allows us to regard the space of quaternionic plurisubarmonic function as a Riemannian manifold. And we computed the Levi-Civita connection of this Riemannian manifold is given by this relation. So something which is, I mean, very natural and very close to the Hermitian case. And from here, it's possible to deduce the geodesic equations. So now the next step, which is still a work in progress, is to put in relation the quaternionic Calabi flow to this Riemannian manifold, putting the picture together, putting this stuff together in order to have a new tool for studying the conjecture. Okay, I think I have only a few minutes, and here there is the last result. I'm still studying with Giovanni Gentili, and I mean the real project is to prove the solvability of the quaternionic motion per equation on compact locally flat HKT manifolds. So considering the theorem of Alesker, and remove from the theorem of Alesker the assumption on the existence of the background HyperKahler metric. So this is in some sense dual to the theorem of Ddg they remove the other assumptions. And we work a little bit on this project by trying to adapt the classical Cherrier proved about the estimates on the estimates of the complex motion per equation. But there is I mean, here is the situation is more difficult because we have some operators which do not commute. So at one point we are stuck in some direction, and if we try to use other techniques we are stuck in other technical difficulties. And very recently we tried another approach by using an analog of the Ddg functional in Kahler geometry, and this was suggested to us by Trusiani in Cogne during a workshop this winter. And actually, by using this approach, it's possible to prove a very nice result, which is about the existence of a weak solution of the equation under our assumptions. So weak means that phi is an L1 function, and I mean, and the next step here should be to try to prove that this function is not of L1 but is actually smoothed. So it's something. So it's the regularization of this result, and here is something which I hope we can do in the next months in order to, I mean, to finish this project and to prove the solvability of the equation under these extra assumptions. Okay, this is the last slide, and these are given by some interesting results, which are, I mean, which are I'm not involved in this project, but they are strictly related to my talk. So the first one is a work in progress of Giovanni Gentili and Nicoletta Tardini, and they study some cohomological obstructions to the existence of HKT matrix on hypercomplex manifolds, and they obtain something which is a little bit deep, like the Massey products in this setting, and they improved some previous results of Lashmi and Weber, which already found some more cohomological obstructions. Another very interesting result is given by Giovanni Gentili, Zhaojiang Zhang, and they studied a large class of elliptic and parabolic equation on HKT manifolds under the same assumptions of Alesker, and their approach includes a generalization of the compensation Hessian equation. So the second item corresponds to two papers, one for the elliptic case and one for the parabolic case. The last one is a paper which is very new. I think it has 1 or 2 weeks, and about is of Li Chen, which gave a new proof of a C0 estimate for equation which it calls of Hessian type in HKT manifolds. So again, this is a paper on very general about the C0 estimates of of the quaternionic motion per equation, but also for a more general class of elliptic equations. So I think my time is finished, so I think I can stop here. So thanks a lot for your attention.
Thank you, Luigi.
Yeah,
Are there any questions or comments? Sorry, what was that?
No, I didn't ask you about the how much time the talk was supposed to do long, but I suppose the 1 hour.
It's
What's
okay.
the standard? It's okay.
I don't remember. Maybe 50 minutes, maybe 1 hour. It doesn't matter.
Okay.
Are there any questions for Luigi? Yes. Simon?
Yes, Luigi, nice talk. Have you, these various conditions on hypercomplex manifolds, HKT manifolds, can you translate the conditions to the twistor space? You know, are there sort of are there conditions on the twistor space that correspond to balanced and all that sort of stuff?
Yeah, I think you can translate, but unfortunately, I don't know the answer. I'm sorry, but
because I remember I think Roger Beliavsky was asking me in the KQT case, you know, I think QKT corresponds to having a contact structure on the twistor space. So it'd be nice if there was some object on the twistor space, because that might give a new way of doing things. I don't know.
Yeah, I think this is very interesting, and yeah, it's of course something which we try to think about, but so far we never considered the twistor space construction in HKT geometry, and actually I don't know, but I'm sure that everything can be described in terms of what happens on the twistor spaces.
Okay, thank you.
Yeah, Luigi, if I remember correctly, in the classical Calabi-Yau, there's the case which is easier, right? Which is when the first Chern class is negative definite. I think the estimates are much easier in that case. Is there, do you know what I mean?
Yeah, but here, when I refer to the classical case, is the case where C1 is vanishing.
So you always talk about vanishing C1, okay.
Yeah, the right analog is the Calabi-Yau case where the first Chern class.
Flat, yes.
Yeah,
okay.
Yeah.
Okay.
So in my mind, balanced HKT corresponds to Calabi-Yau manifolds. Yeah, that's my what I. Yeah. So the analogy is here is when the differential class is vanishing.
Other questions for Luigi? Well, if not, let's thank him again for a very nice talk.
Thank you.
And I'll stop the recording now.